Afternoon, everyone. Today,
Good afternoon.
today's talk, good afternoon. Today's talk is presented by Dr. Urmila Chaudhary, madam. Her research area are supply chain, inventory modeling, and infectious disease. She has been selected as a top 15 researcher in the field of her research area from all over the world. She has published more than 25 papers, and all are in the reputed journal. And most of the research paper are in Scopus and SCI index. Or H index and I index are 10, and the total citation are 263. She also published book in the international publication. She is reviewer in many highly indexed journals. She has taken many professional training at the national level. Today, she is going to present on mathematical modeling of infectious disease. Now, Urmila madam, you can start your session. We welcome you.
Yes,
Uh, 1 second. Sir, you are not started the recording. Yes, am I audible?
I
Okay, no problem. Urmila madam, just start the presentation and just call the person. Okay,
yes. Good afternoon, all of you. Chirag said just 2 minutes.
no problem, no problem, madam. All of you just wait for 2 minutes. Madam will come.
Hello.
Yes, madam. You are audible.
Am I audible?
Yes, yes.
Okay. Sorry for that. Good afternoon, all of you. Myself, Dr. Urmila Chaudhary, and my research area is inventory modeling. But in the earlier year, there is another area that is infectious disease or mathematical modeling of infectious disease. So basically, I'm the person of inventory modeling. But after taking the Viva of MS student, I realized that I will present on this topic like mathematical modeling of infectious disease because there are three, four presentation on this topic, but student not clear about the mathematical modeling or how it is developed from the disease and what will be the procedure of to check the stability of the model. So here I present on this topic mathematical modeling of infectious disease. So today I am presenting on mathematical modeling of infectious disease. And right now I am a lecturer at Government Polytechnic Dahod. Talking about mathematical modeling of infectious disease, you need to know what is infectious disease because you don't know very well infectious disease or symptoms or precautions or some control for infectious disease, then you can't develop a mathematical modeling of infectious disease. So first of all, here I explain what is infectious disease. So infectious disease can be caused by many python, including bacteria, virus, fungi, and parasite that may be caused illness and disease. Means infectious disease may be spread from person to person directly or via reservoir like mosquito, tick. Via reservoir, any person may infect by another person via reservoir or directly from the reservoir. So this is the infectious disease. Now, how it spread? It's two type spreading. But before this, you know very well that you have to know very well about the your disease is epidemic or pandemic. So, what is the meaning of epidemic? Epidemic is a disease that affect a large number of people within a community or population or region. Means if one state or one village affected by one disease, then it called epidemic. Like yellow fever, smallpox, polio are the example. Now, what is pandemic? Pandemic is nothing but what? It's a epidemic itself, but that's a spread worldwide over a multiple of countries or continent. It's mean a virus cover a vital area affecting several countries and population like COVID-19. You know very well COVID-19 spread in more than many countries like China, India, USA, Canada, Europe, all countries. So it's nothing but pandemic. Means your spreading area is wider than it's called pandemic, or it's smaller than it is called epidemic. Now, types of transmission, because we are talking about the infectious disease, infection. So there are two type of transmission of infection. One is vertical transmission and another is horizontal transmission. Now, vertical transmission is nothing but what? a infection via infection of a child via mother, like before birth, after birth, that is vertical transmission. And horizontal transmission is nothing but this our like plague, COVID-19. These are the horizontal transmission. So here there is one YouTube video that I want to show you here. Can you hear video?
I think video is paused.
This is it's okay. Okay, no problem. See, basically we have a two types of in horizontal transmission. If I talking about mathematical modeling, then we have a two types of model. One is stochastic model, another is deterministic model. So here I'm the person of mathematics, I have not a background of statistics, so I go for a deterministic model. So first of all, what is the need of mathematical modeling of infectious disease? So this is the important part. You need to know about this. Means why we model that infectious disease. So modeling of infectious disease is tool that has been used to study the mechanism by which disease spread to predict. Means first reason is what we can predict the future of the disease, outbreak of the disease, and another is we can evaluate the strategy to control an epidemic. Means we can control that for controlling. We can add some vaccination, or we can take some precaution, and we can break the chain of that spreading. So for that, we have to develop a model, mathematical model, and if we take some parameters and apply some control on that model, then we can definitely uh, meet some solution of to control a infectious disease model, an infectious disease. So first of all, here is type of epidemic model. So I already say that there are two types of model. One is stochastic, another is deterministic. So generally, the deterministic model is nothing but what it's a SEIR model. SIR model, SES model. So generally people working on this model, these are the basic model. So in the deterministic model, when dealing with a large population, and deterministic or compartment mathematical model are often used. And in this deterministic model, individual in population are assigned to different subgroup or compartment. Means in the deterministic model, we have to assume some compartment. Like if I talking about SEIR model, so there are four compartment. One is a susceptible compartment, another is exposed, third one is infectious, fourth one is recovered class. So first of all, we need to know, here I explain only SEIR model because we have a limited time. So I explain here SEIR compartment model. So what is S? So S is the fraction of susceptible individuals, means those able to contract the disease or meet the disease. E means what? E is the fraction of exposed individual, means those who have been infected but not are not yet infectious. Means ये दूसरे को अभी infection नहीं लगा रहे but just infected है. Like we are talking about, if we can talk about COVID-19, then my RT value is 31, then I am infected but not infectious. Then I'm go for the I class, that's the infectious class. Means मेरी बॉडी में से इन्फेक्शन दूसरी बॉडी में हो सकता है, कॉन्टेक्ट होने से दूसरे में स्प्रेड हो सकता है. So I is the fraction of infective individuals, those who capable of transmitting the disease. Means वो transfer easily कर सकता है. As I say, if your RT value is 15 to around 26, then it's a sprayable zone, and after 27, it's a exposed class, means infected but not yet infectious. And R is the fraction of recovered individual, those who have been immune, recovered from the disease. So these are the four class, SEIR. Now here, let's see the transfer diagram, SEIR. Now here I take one example, how we develop a mathematical model from this diagram. So see, if I take one example, we have a 4. So in the one classroom name is S, another is E, another is I, and another is R. So first of all, if I say in the S class, we have a 20 people. In this 20 people, if I say that the 0.2 rate, at the 0.2 rate, some people go transfer from S to E, means 20 people is there. So if I say 4 people transfer from S to E, or 5 people transfer from S to E, after some time, in this 4 to 5 people, 3 to 4 people transfer from E to I with key rate. With rate. Infectious. And after second, some precaution or some people transfer from A to R, that is recovered class. So another people recover from the infection. So that will be goes on R class. So this is the transfer diagram. From this, we have to develop a mathematical model. So here it is with the time, all the class rate of change will be there. So if I say first rate of change of first class is ds by dt, then what is ds by dt? So ds by dt is nothing but what? Initial birth. Initial birth means I have already say that 20 people in S class. So initially lambda is your initial 20, means your birth rate. lambda. And after the contact with infectious, some people transform from S to E, that with beta rate. So it's nothing but what, minus beta Si. And this is the death rate, natural death rate. Means between the 20 people, one or two people suffering from the other like diabetes or heart attack, it's a natural death. So some percentage of people will be died from natural, uh, already been suffering from some um, another disease. So it's will be nothing but what, minus mu s. So rate of change of susceptible class is what? Birth minus contact rate with infectious, that is minus, and then minus of your natural death rate. So finally, this is your equation of ds by dt. Now, what is the second equation of second E? So this people goes from S to E, that is BSI. So these are the adding in the E. And minus KE. KE means what? Some people infected after the exposed class. So minus KE, and these are the adding in DAI by DT class, means I class. And minus mu E, that is the natural death of in the exposed class. So finally, this is the rate of change of exposed class, that is plus, which are coming from S class, that is plus sign, with plus sign, and minus K plus mu, that is nothing but what? After infection, this is this population move from E to I, that will be minus, and here it is plus KE because move from E to I. And finally, that is natural death in those class. And similarly, in the infectious class, uh, uh, coming from E to I, that is KE, so that's why it's a plus. And minus gamma I, it's a infection, after infection, it's a recover class. So transfer from I to R, with the gamma rate, it will be recovered. So from I to R, it will be transferred. So here it is minus gamma I, and in the R class, recovered class, it's a plus gamma I, and mu I and mu R is the our natural death rate in each class. So here it's a basic model of SEIR. But once you understand this basic model SEIR, then you can add in this model, like if you take vaccination or some precaution, you can add in by class. You can plus something, means plus minus using vaccination. Some people recovered and transfer from I to E. So you can add vaccination also. You can add some precaution, or you can add some with the environmental changes. Suppose infection will be increased, then you can also minus and add from E to I. So once you understand this basic model, then you can change the equation with some parameter, and you can add all the assumption. You can take all the precaution or vaccination or some environmental changes. Then you can develop another model for the disease. But first of all, you have to uh, know about the disease and what are the possibility to control that disease. Then you can develop this different system of differential equation from the real life. So this is the birth rate. It's a natural death rate, and this is the contact rate of susceptible and infected people. This is the infected rate, and this is the death rate of infection. So here, now we are talking. Now we will discuss for this system of differential equation, what are the stability of this system of differential equation, or how can we solve or how can we control this system. So for that, see, our interest in what, only on exposed class and infectious class and susceptible class, because after recovery rate, we are not interested in that disease. So here we have a no transfer from recovery to compartment back to the susceptible. We will analyze the first three equation only, because there is a no meaning to discuss or to evaluate the recovery class. So here we take only three classes: susceptible, exposed, and infectious classes. So what is the solution procedure? So here I discussed the one of the solution procedure from the research paper. Hefferman provide a nice readable introduction for calculating R0, because see, R0 is very important for the any infectious disease mathematical modeling, because R infectious disease only. R0 is a reproductive number. So with the help of I0, we can control the particularly infectious disease. So how can we evaluate the R0? So this is the procedure. Uh, our first step is what? Find out the FI and VI. Now there is a question, what is FI? So FI is nothing but new infection. New infection means what? See, this beta Si plus, that is a new infection in exposed class. So this is our Fi, beta Si only, it's our Fi. And another is Vi. Vi is what? Transfer of infection from one compartment to the another compartment. So this Ke and gamma I, this is the infection from one compartment to another compartment. To know Fi and Vi from the system of differential equation. After that, you have to find out the X0. X0 is what? Disease-free equilibrium. Means initially, if we assume that there is a no disease, then what will be our initial point? You have to derive this initial point X0. And then you have to derive that capital F and capital V. So what is capital F and capital V? Is nothing but partial derivative of Fi and Vi with respect to Ei and S. Xi is a vector. It's nothing but what? Ei, and Si. Okay. So with respect to Ei and S, we have to differentiate Fi and Vi vector. Then we will get one Jacobian matrix. And after that, once you find out the capital F and capital V, we have to find out V inverse and then multiply with F and V inverse. And we are getting G. And once you find out the eigenvalue, then one dominant eigenvalue is nothing but R0, that is our reproductive number. R0
some network issue is there. So madam will join us in few minutes.
Hmm. Am I audible?
Yes, ma'am.
Yes,
Yes.
audible. Yes.
Hello. Hello.
Yes, madam. You are audible. Yes, you are audible, madam.
Okay. Am I audible?
Yes, madam.
Can I start?
Yes, yes.
Okay. ठीक है एक काम करें मृदुल फोन करें की तथा हमारा कहीं पर डाउट है तो मैं फोन कर हमारा नेटवर्क कट गई okay sorry so see our total population is what addition of three classes S E I that is S plus E plus I equal to some constant number total population once you apply the derivation with respect to t on the both the sides so we will get di by dt of s plus e plus I is equal to what 0 because derivation of constant with respect to t is 0 so we have an equation that's d dt plus de by dt plus di by dt equal to 0 so if I add our right hand side of this equation we will get what finally that is lambda uh, and initially this is free equilibrium. So we know that there is no population in E class, there is no population in I class. So here I take E and I will be 0. Then finally we will get what? Lambda minus mu s is equal to 0. If I add this three equation of right hand side, then finally we will get lambda minus mu s equal to 0. So finally, we have a population, initially population is lambda upon mu. So using this technique, we can find out this x0, this is free equilibrium point. We can easily find out. After that, you have to differentiate in model, that is is the equation di by dt and di by dt with respect to S, E and I. Means here I take only infectious class, that is E and I. Totally infectious class is E and I. So here I take two class only, dE by dt and di by dt. So look at here, in this two equation, dE by dt and di by dt, you have to differentiate dE by dt with respect to I and E, and di by dt with respect to I and E. So you will get this F and V. Sorry, EI and S with respect to EI and S. So you can find out this F and V, that is our capital F and V. And once you find out inverse of V, like adjoint of V upon determinant of V, that is V inverse. So you can easily multiply F and V, that is our generation matrix G. And we can say that here there is a mistake. R0 is nothing but what? Largest dominant eigenvalue of F of V inverse generation matrix G. So once you multiply with F and V inverse, you have a one matrix of 2 cross 2, and you can easily find out the eigenvalue of that matrix, that is the generation matrix. And that maximum, that dominant eigenvalue is nothing but reproductive number R0. So we can easily find out this R0 from of any system of differential equation or any model of infectious disease. Now, how it works R0 or important R0 for models. So the disease-free equilibrium X0 is a locally accepted stable if all the eigenvalue of R0 have positive real number. But see, once you analyze the disease, you have to find out R0. Because if you get R0 is greater than 1, R0 is greater than 1 means your eigenvalue of generation matrix F of V inverse matrix is greater than 1, then disease will be epidemic. Means उसके लिए आपको कोई कंट्रोल लगाने पड़ेंगे, कोई वैक्सीनेशन लानी पड़ेगी, या तो कोई प्रिकॉशन लेने पड़ेंगे, क्योंकि वो एपिडेमिक है यानी स्प्रेडेबल है और वो वाइड एरिया में एपिडेमिक कन्वर्ट इनटू पेंडेमिक. So if you get R0 greater than 1 for any infectious disease, you have to control that disease. But if you get R0 less than 1, then disease will died out soon. So उसके लिए फिर आपको कुछ करने की जरूरत नहीं है. तो ये its reproduction number is important for you in both ways. Once you analyze the disease or once you find out the control for disease, it's help in the sense of R0 greater than 1, then you can apply vaccination or precaution. And after that, once you again find out the R0 and less than 1, then you can satisfy, yes, okay, after this control, disease will be died out soon. So reproduction number is very important in this modeling. So there is one theorem also. Disease-free transformation model given by 1 with X. If X0 is a disease-free equilibrium of the model, then X0 is locally acceptable stable if R0 less than 1 and unstable if R0 greater than 1. If our system is unstable, then we have to add some control, and we have to control this system and convert into a stable system. So once you find out this R0, you can easily analyze further. Now second one is endemic equilibrium. Means you have, suppose you want to analyze all different classes of behavior. Then how can you analyze? So if you say the rate of change of each classes will be zero, means df by dt, de by dt, and di by dt is equal to zero, then right hand side will be as it is, and left hand side will be zero. Then you have a system of equation. Then you can easily find out the solution of the system of equation, and you can easily find out our unknown, that is S, I, and E, the three compartments. And this we can consider all the rate of change zero, then we can get system of equation. So finally, we will get the S star, E star, and I star. And once you plot this S star, E star, and I star with respect to time, you will get the plot with respect to time. So you can analyze the behavior of each class. Once your time will be changed, what will be the behavior of each class? So you can analyze using this endemic equilibrium. So this is another part of the stability. So behavior of during pandemic, epidemic, आप इजीली एनालाइज कर सकते हो हर एक क्लास को कि नेक्स्ट बिहेवियर क्या हो सकता है. प्रेडिक्ट, यू कैन प्रेडिक्ट द बिहेवियर ऑफ डिसीज इन ईच क्लास. So these are the reference. This is my one of the paper on which Japanese encephalitis means brain fever. So these are the, we can say that it's not a person-to-person infection, but via reservoir infection. So see, in this my paper, there are 13 equations, and this is the transfer diagram of human population, and transfer diagram mosquito and reservoir population. Means see, once you talking about infection from person to person, you have a one diagram. But if you are talking about the person to some mosquito, and through mosquito you have a disease, so you have a you have to draw two diagram, and from this you will get this equation like this susceptible class, birth class minus contact rate minus natural death. So see, once you see all the papers, all equation are same because modeling is same, but difference is what you can add your assumptions, or add your vaccination or some control in the equation, because SEIR model is same, calculation is same, but what will be the change is आप जो कंट्रोल डाल रहे हो कि भाई ये डिसीज को मुझे कंट्रोल करना है, तो ये कंट्रोल मैं डाल रही हूँ. इन्फेक्शियस डिसीज में मैं ये वैक्सीनेशन डाल रही हूँ, वो टर्म ही एक्स्ट्रा ऐड होंगे. और चेंज क्या होगा कि डिसीज टू डिसीज वेरी क्या होगा, डेथ रेट है, ये जो पैरामीटर्स है आपके आगे के, अल्फा है, बीटा है, ठीक है, इन आवर प्रेजेंटेशन that is nothing but E and K and gamma and all the parameter आपके क्या होंगे, चेंज होंगे. बाकी मॉडल सेम ही रहेगा, और आप कंट्रोल चेंज कर सकते हो अंदर जो आपको कंसीडर करना हो, पर उसके लिए आपको वो डिसीज के बारे में पढ़ना पड़ेगा कि हाउ कैन वी कंट्रोल दैट डिसीज पर्टिकुलरली. So you can easily find out this R, F, and V, and Jacobian matrix, and reproduction number, and eigenvalues, and stability. And from this using MATLAB simulation or MATLAB programming, you can find out the behavior of all classes. Endemic equilibrium using this simulation also. And see, these are the two way. One is what you can find out the S star, E star, I star. It's a endemic equilibrium variable, or you can use this MATLAB simulation, put all these parameters, and you can find out this graph of all the classes easily. And you can analyze the behavior of this classes uh, with respect to time. So similarly, um, my main point is what model is same, but there are changes in parameter only. See, this is one of another paper. This is another paper of this vector bond disease, SEIR model and simulation. So here it is malaria disease problem. See this one. So these are the equation of SEIR, and then you can find out the solution, reproduction number. All these papers. So these are my references with the help of this HIV. So HIV is a vertical transmission. If I say a born child, a newborn baby have infected from her mother, then it's a vertical transmission. So see, these are the class equation S dot I dot A dot Q dot, and this is the generation matrix and reproduction number also. See, R is the reproduction number. It will be greater than 1, so it's a epidemic. So you have to take some control for this disease. So you can analyze from this MATLAB programming all the classes. Okay. Um, these are the hmm. Now conclusion of session, we can say that after analyzing disease, one can develop a mathematical modeling. If you want to develop a mathematical modeling of disease, so you have to first of all know about the all symptoms and precaution or some control for disease. And with the help of this, we can predict the outbreak of the disease, and we can evaluate the strategy to control the epidemic, and one can apply prevention, vaccination, and analyze impact of vaccination also. So thank you. Now everybody have a mobile.
Yes, ma'am. Yes.
Yes.
So see, here I have a one quiz on this. So on your mobile, on the Google Chrome site, you have to write kahoot.it. All of you, please write down kahoot.it. If this works, because network is not good. Okay. Okay, all of you ready for that? Write down kahoot.it and open it. Kahoot.it, not kahoot.com, okay? Write down the kahoot.it in your mobile. Kahoot.it. Now enter this pin, display pin. Hmm. Huh. Enter this pin 3280712. Once you enter this pin in kahoot.it site, you can easily enter this quiz. Okay, Drashti, Ashok, Bhumi. Okay. Once you enter, you can show your name on the this display screen. Bhumi, Manish, Leela. Okay, Chirag. Okay, can I start? Here display a question and option. In your screen only a symbol of the option. So you can take a right answer or symbol. Means your answer is triangle, then tick triangle or square or circle. Then you can tick correct answer. Tick. COVID-19 is epidemic disease, pandemic disease, or none of this. Tick the symbol. Right answer symbol. In your screen only symbol, not options. Option only. So that. Okay. 11% are correct into. Okay, next. So there are points. So अशोक सर ने फास्ट आंसर किया है. तो जितना फास्ट आंसर दोगे उतने पॉइंट्स आपको रहेंगे. नेक्स्ट क्वेश्चन. Malaria is pandemic disease. True or false? Okay. Very good. Okay, next question is an epidemic that becomes unusual, widespread, and even global in its reach is referred to as. Okay, very good. Okay, which of the following things cause malaria? Or you can say reserve here. Tick, plasmodic, red blood cell, or mosquito. Yeah. Okay, so Ashok sir is second runner-up. Katie is the first runner-up, and Bhumi Patel is the first one. Winner of this quiz is Bhumi Patel. Congratulations. Thank you. So this is from my side.
Hello, am I audible?
Yes,
Hello,
sir. Yes, sir. Yes, sir.
ma'am, I have one question. Hello, Urmila ma'am.
Hello.
Yes, ma'am.
एक हाँ
Hello,
आवाज नहीं आ रही.
hello,
हम्म.
hello.
आवाज क्यों नहीं आ रही? हम तो आवाज नो ऑप्शन ना तो ये पे लोग ये क्या आवाज okay thank you
Hello,
this is from
hello.
my side.
Am I audible to you, ma'am?
Yes.
Ma'am, actually, I joined late in the meeting, so that's why I don't know about R naught. Can you please explain again what is R naught actually? R
R
zero.
naught is a recovered class. R naught is a recovered class. R naught, okay. R naught is reproductive number.
Okay,
So that is not a, it's only a number, non-unit number. There is no unit of R naught because it's a ratio of two rate. That will be birth rate upon death rate. Ratio of two rate. So R naught is
okay,
what? Total number of birth rate upon total number of death rate initially. Then after infection it will be changed, but it is nothing but what? Largest eigenvalue of generation matrix, FV inverse. And that eigenvalue will be greater than 1. So your disease will be epidemic, means वो spread होता जाएगा और जो ज़्यादा spread हो गया तो वो pandemic हो जाएगा. That means COVID-19. ओके तो
okay, ma'am.
आर नॉट ग्रेटर देन 1 आया मीन्स आपको उसमें उसको कंट्रोल करना पड़ेगा, नहीं तो वो बहुत स्प्रेड होगा जैसे कोविड-19 हुआ. और कोविड-19 के केस में कोई जल्दी कुछ क्यों नहीं कर पाया? बिकॉज इन एवरी कंट्री आर नॉट इज डिफरेंट इन कोविड-19. तो दैट्स व्हाई दे कांट कंट्रोल. सपोज हमसे कंट्रोल हो गया, दूसरी कंट्री से नहीं हुआ है बिकॉज उसका आर नॉट अलग है. तो इन द रिगार्डिंग कोविड आर नॉट हर एक कंट्री का अलग अलग था, बर्थ रेट एंड डेथ रेट. तो वो आप आर नॉट की हेल्प से इजीली कैसे वो डिसीज को कंट्रोल करना है वो जान सकोगे. लेस देन 1 आया तो आपको कंट्रोल करने की कोई जरूरत नहीं, वो अपने आप थोड़े टाइम चला जाए, विल बी ओके. बट ग्रेटर देन 1 तो आपको उसको कंट्रोल करने के लिए दो तरह का आपको प्रिकॉशन, या तो प्रिकॉशन के लिए हम कोविड में जो प्रिकॉशन लेते हैं वो मास्क, हाथ करते धोते हैं, वो प्रिकॉशन लिए आपने, वो DI/DT और वो क्लास में आप ऐड करके प्रिकॉशन देख सकते हो. और या तो फिर वैक्सीनेशन ऐड किया तो आफ्टर वैक्सीनेशन आप अगेन रिप्रोडक्शन नंबर चेक करो और वो लेस देन 1 आता है, इसका मतलब क्या है कि आपका डिसीज जो है वो कंट्रोल हो जाए वैक्सीनेशन। तो वो आप रिप्रोडक्शन नंबर इज व्हाट, बर्थ डेथ रेट, तो उसको कंट्रोल करने के लेस देन है तो नो प्रॉब्लम, ग्रेटर देन 1 है तो वो प्रॉब्लम है। ठीक है।
ओके मैम, क्या मैम उसमें चांसेस है इक्वल टू 1 आने के?
हाँ, इक्वल टू आने के चांसेस है, इक्वल टू आने
ओके
के चांसेस है। वो मैंने आपको एक पेपर नहीं दिखाया, एक पेपर में वो भी
ओके
है इक्वल टू आने के चांसेस, उसको भी पर अनस्टेबल ही बोलते हैं इक्वल को भी,
ओके, मीन्स वी वांट स्ट्रिक्टली लेस देन।
स्ट्रिक्टली लेस देन 1।
ओके मैम, थैंक यू मैम, थैंक यू। Any other questions from audience? Okay ma'am, thank you so much for your valuable speech ma'am.
ओके, थैंक यू।
Hello, thank
ओके।
you so much ma'am.
ओके, बाय।
Bye ma'am, thank you.